Is teleportation possible? Could a baseball transform into something like a radio wave, travel through buildings, bounce around corners, and change back into a baseball? Oddly enough, thanks to quantum mechanics, the answer might actually be yes. Sort of. Here's the trick. The baseball itself couldn't be sent by radio, but all the information about it could. In quantum physics, atoms and electrons are interpreted as a collection of distinct properties, for example, position, momentum, and intrinsic spin. The values of these properties configure the particle, giving it a quantum state identity. If two electrons have the same quantum state, they're identical. In a literal sense, our baseball is defined by a collective quantum state, resulting from its many atoms. If this quantum state information could be read in Boston and sent around the world, atoms for the same chemical elements could have this information imprinted on them in Bangalore and be carefully directed to assemble, becoming the exact same baseball. There's a wrinkle, though. Quantum states aren't so easy to measure. The uncertainty principle in quantum physics implies the position and momentum of a particle can't be measured at the same time. The simplest way to measure the exact position of an electron requires scattering a particle of light, a photon, from it and collecting the light in a microscope. But that scattering changes the momentum of the electron in an unpredictable way. We lose all previous information about momentum. In a sense, quantum information is fragile. Measuring the information changes it. So how can we transmit something we're not permitted to fully read without destroying it? The answer can be found in the strange phenomena of quantum entanglement. Entanglement is an old mystery from the early days of quantum physics, and it's still not entirely understood. Entangling the spin of two electrons results in an influence that transcends distance. Measuring the spin of the first electron determines what spin we'll measure for the second, whether the two particles are a mile or a light year apart. Somehow, information about the first electron's quantum state, called a qubit of data, influences its partner without transmission across the intervening space. Einstein and his colleagues called this strange communication spooky action at a distance. While it does seem that entanglement between two particles helps transfer a qubit instantaneously across the space between them, there's a catch. This interaction must begin locally. The two electrons must be entangled in close proximity before one of them is transported to a new site. By itself, quantum entanglement isn't teleportation. To complete the teleport, we need a digital message to help interpret the qubit at the receiving end. 2 bits of data created by measuring the first particle. These digital bits must be transmitted by a classical channel that's limited by the speed of light, radio, microwaves, or perhaps fiber optics. When we measure a particle for this digital message, we destroy its quantum information, which means the baseball must disappear from Boston for it to teleport to Bangalore. Thanks to the uncertainty principle, teleportation transfers the information about the baseball between the two cities and never duplicates it. So in principle, we could teleport objects, even people. But at present, it seems unlikely we can measure the quantum states of the trillion or more atoms in large objects and then recreate them elsewhere. The complexity of this task and the energy needed is astronomical. For now, we can reliably teleport single electrons and atoms, which may lead to super secure data encryption for future quantum computers. The philosophical implications of quantum teleportation are subtle. A teleported object doesn't exactly transport across space like tangible matter, nor does it exactly transmit across space like intangible information. It seems to do a little of both. Quantum physics gives us a strange new vision for all the matter in our universe as collections of fragile information, and quantum teleportation reveals new ways to influence this fragility. And remember, never say never. In a little over a century, mankind has advanced from an uncertain new understanding of the behavior of electrons at the atomic scale to reliably teleporting them across a room. What new technical mastery of such phenomena might we have in 1,000 or even 10,000 years? Only time and space will tell.